Hi everyone, now we are at lecture number 4, Multivariable Calculus. This is continuation to last lecture, lecture number 3. Problem number 7. So let us find partial derivatives, first order partial derivatives and second order partial derivatives, where f is x into cos y and y into e power x. Okay. So these are first and second order partial derivatives. So first fx. So that means dou f by dou x, right? Dou f by dou x. With respect to x, you have to do. So dou by dou x of what is f now? Substitute back x cos y plus y into e power x. Okay. Now, so with respect to x you are doing, therefore you have to treat y is constant, right? Y is constant, because with respect to x you are doing y constant. Okay, yeah. So x into cos y derivative, y is constant, therefore cos y is constant, x derivative is 1. So 1 into cos y, 1 into cos y, right? Plus with respect to x, therefore y is constant, so y as it is, e power x derivative e power x. So this is cos y plus y into e power x. So this is fx. Okay. Next one, fy. With respect to y, now x is constant. That means dou f by dou y. That means dou by dou y of what is f x cos y plus y into e power x. So in this x constant, because with respect to y you are doing, you have to treat x is constant. Okay. So now since x is constant here, so x as it is cos y derivative minus sin y. So minus x into sin y. I am not touching x as it is, but cos y derivative only I am doing with respect to y, cos y derivative minus sin y. Derivative, not integration. Okay. Next, plus with respect to y, so y derivative is 1 and e power x is constant. I am writing as it is. So it's like, for example 2x. What is d by dx of 2x? So since 2 is constant, 2 as it is, and x derivative is 1, like that. So answer is 2. Same like that. Since x is constant, so e power x as it is, and y derivative is 1. Okay, this is dou f by dou y. Next one, fxy. That means what? First with respect to x. Okay, first with respect to x, next with respect to y. Order. So therefore, first with respect to x, therefore fx, first fx. After that, with respect to y. Or you can do like this also. All these are notations. Dou by dou y, because with respect to y, second. First with respect to x, therefore dou f by dou x. So this is the notation. So in this first with respect to x you are doing, after that with respect to y. So okay, from right to left you have to move. First with respect to x, second with respect to y. Same thing. Well, first with respect to x, second with respect to y. Now replace back. So dou by dou y of. So already I have done dou f by dou x. Look at first one is a dou f by dou x. Its value is cos y. This time replacing cos y plus y into e power x. Okay. So if you want, you can write this is 1 and this is number 2. So since we are using 1. Okay. Next one, this is dou by dou y of. So with respect to y you have to do, therefore obviously x is constant here. X is constant. Not only x, remaining all are constant in this. Okay. If it's a 3 variable function, with respect to y you are doing, therefore x and z constant. Since it is 2 variable function, so with respect to y you are doing, therefore other variable x is constant, like that. Okay. So then, yeah, with respect to y, so cos y derivative minus sin y. Okay. and y derivative is 1 into e power x. So overall this is minus sin y plus e power x. So this is what fxy. Okay, next one f yx. That means first with respect to y, next with respect to x. So it means again first with respect to y, therefore fy first, after evolution of fy, then with respect to x, or simply dou by dou x of first with respect to y, therefore dou f by dou y first, dou f by dou y, because first with respect to y. So now dou by dou x of what is dou f by dou y? By using equation number 2, minus x sin y. Already this one I have evaluated, that's why directly I am substituting. So since by using equation number 2, just I am substituting back, that's it. Now with respect to x you have to do, so minus sin y, x derivative is 1, sin y is as it is, and e power x derivative is e power x only, that's it. So this is first and second order partial derivatives. Okay, next one, problem number 8. Show that the function f of x comma y, this one is not continuous at origin, but partial derivatives fx fy exist at origin. So in general, if it is a single variable function, a function is not continuous at some point, derivative does not exist, right? But in partial derivative it is not like that. Function is not continuous at some point, but partial derivatives may exist. It doesn't mean that always exist, may exist. So this is one of the examples. So now let us prove that first. What I need to prove? It is not continuous at origin. So what to do again? By using continuity definition. First, x naught y naught is what? Now what is x naught y naught? So x naught y naught is 0 comma 0. Okay, and what is f of x naught y naught? So first point in this, f of x naught y naught, function should be well defined at this point, right? That means f of 0 comma 0. So direct substitution, look at f at 0 0, function value is 0, so therefore 0. So defined, or simply it is finite, defined. So first condition satisfied. Second condition, I want a limit value, right? So limit x comma y, and this one is reaching to x naught y naught fxy, two variable function. So this can be written as limit x comma y reaching to x naught y naught means origin 0 comma 0, isn't it? And fxy, so x into y upon x square plus 2 times y square. This is fxy. Now substitute the limit. What will you get? X is 0, y is 0. So 0 by 0 you are getting. Okay, then go to either simplify the function or go to path limits. Okay, so then function cannot be simplified because no similar terms in the numerator and denominator. Therefore directly I am going to the path limits. So then in path limits, what we have to do is I have to select a path, two different paths I need to select. Along that two different paths, the function has to reach to 0 comma 0. Now I am choosing the path. If I choose y is equal to mx, here x square will comes, here also x square will come. So therefore along y is equal to mx I am choosing. If I choose y is equal to mx, so x into mx upon x square plus 2 into mx whole square. Okay, then what will you get? So limit x comma y reaching to origin along y is equal to mx path. Okay, y is equal to mx path. So numerator x square is out, so what will remain is my, denominator also x square is out, 1 plus 2m square. So therefore what is the limit value now? This limit value is exactly equals to, what is that, m by 1 plus 2m square. So therefore limit value is depending on m. It is depending on m means what? It is depending on path, y is equal to mx path. So therefore limit value, therefore limit is depending on limit does not exist. So once limit does not exist, so therefore what is conclusion? So third point is, so limit x comma y reaching to origin of the function f of x comma y is not equals to f of x naught y naught. What is f of x naught y naught? Which is 0. This value is 0, but which is not equals to. Therefore conclusion is f of x comma y is not continuous at 0 comma 0. It is not continuous at 0 comma 0. Okay, next one. Now let us move on to the fx at 0 0 and fy at 0 0. I need to show that these two exist. Okay, I need to show that these two exist. So first, how to calculate fx? Fx is nothing but dou f by dou x. So you can do in two ways. First is, say I want fx, right? Fx means partial derivative with respect to x. Already f is given to you. U by v method you apply, you find out what is fx. After that you substitute the point 0 comma 0. Next again similarly fy. Again f of x comma y is given to you. It is a fraction. X into y is a numerator. X square plus 2y square is a denominator. Then do partial derivative with respect to y. Okay, do partial derivative with respect to y. You will get some answer. In that you substitute x is 0, y is 0, so that you will get fy. So that is one way. The second way is the simplest way, that by using principle. What is dou f by dou x? So limit h tends to 0, variation in x. Therefore f of x plus h comma y minus f of x comma y divided by h. This is 1. But what I want? Fx at origin, right? So fx at 0 comma 0 I want. That means what? Dou f by dou x at the point x naught y naught, which is 0 comma 0 I want. So that means which is, so limit h tends to 0. Okay, now instead of x naught, let me write first x naught y naught, so that x naught y naught, I will write the formula first. X naught y naught, x naught y naught, what is that? F of x naught plus h comma y minus f of x naught y naught divided by h. Okay, now so instead of x naught y naught you are having origin, so therefore this becomes, so since x naught y naught is origin, so therefore so fx at origin, fx at 0 comma 0 are simply dou f by dou x at origin. At origin is nothing but limit h tends to 0, yeah, f of 0 plus h comma 0 minus f of 0 comma 0. Wherever x naught, there you write 0, wherever y naught, there you write 0. Okay, now this is, what is fxy? Let me write here. Fxy is, f of x comma y is, what is that? X into y upon x square plus twicely y square. Okay, so same thing, let us proceed here. So limit h tends to 0, yeah, what is this? F of h comma 0, right? F of h comma 0. So wherever x, there you write h, wherever y, there you write 0, minus f of 0 comma 0 upon h. Yeah, simplify this, what you will get? So limit h tends to 0, yeah, f of h comma 0. In this x, instead of x you write h, instead of y you write 0, instead of x you write h square plus 0. So 0 by h square is 0 minus. Next, f of 0 comma 0. What is f of 0 comma 0? It is 0 only, because function is defined at 0 comma 0. I am not substituting x is 0, y is 0. It is not like that. Function is defined if x comma y not equal to 0. This is the function value. If it is equal to 0, if it is equal to origin, the function value is 0. Therefore, if it is equal to 0, function value is 0. That's what I am substituting here, 0. Do it by h. Now what is this? 0 by h is 0. Therefore, existed. Similarly, same thing for fy. Again same at origin, 0 comma 0. Okay. This is dou f by dou y at origin. Again, by using first principles, this will be equals to limit h is reaching to origin. So directly I am substituting f of 0 comma 0 plus h, because variation in y coordinate, minus f of 0 comma 0. Okay, 0 comma 0 upon h. That means which is limit h tends to 0. Okay, h is reaching to 0. F of 0 comma h minus f of 0 comma 0 whole upon h. Now substitute back. What is f of 0 comma h? So wherever x, there you write 0, instead of y you write h. So 0 by 0 square plus 2h square. So 0 only it is. So 0 minus 0 by h, and where limit h is reaching to 0. Now this is again 0. Look at, both are existed. So therefore, what is the conclusion? Conclusion is, look at this, fx at 0 0 is nothing but fx at 0 comma 0. Okay, is 0, and what is fy? Fy at 0 comma 0 is again 0. Therefore existed. So this function is not continuous at origin, but first order partial derivatives existed at 0 comma 0. Okay, this is the conclusion. So you can do this fx and fy, first order partial derivatives fx and fy directly, because already function fxy is given to you, and apply directly fx. What is dou f by dou x? Dou f by dou x is nothing but dou by dou x of this one. So since it is a u by v method, then apply u by v method and do it. You will get a fraction, and there you substitute x is 0, y is 0. It becomes somewhat lengthy because it is a fraction and some multiple functions. So instead of doing that, if you want to make it simple, then apply this by using first principle like this. Both are correct. Directly by doing derivative and substitution 0 0, or by first principle like this. Okay, you can do in any of the way. Next one. For the function f of x comma y, x into y 2x square minus 3y square upon x square plus y square, it is not it is defined when x comma y not equal to origin, and if whenever x comma y is equal to 0 comma 0, function value is 0, and show that the second order partial derivatives at origin are not equals. So this I want to prove by using principles. Okay, first principles. So before that, here what is x naught and y naught? So x naught and y naught is origin, right? It's not required because we are not showing continuity. Okay, it is origin. And here, first with respect to x, next with respect to y, you do derivative of this function, then substitute 0 comma 0. This is direct method. Or first with respect to y, second with respect to x, do derivative of this one, then substitute x is 0, y is 0, then you will get this value and show that both are not equal. So this is one of the way. Second way, by using principles, by definition of partial derivative. Okay. So first, fx at origin. Okay, or simply dou f by dou x at origin. X naught y naught is origin. So now this is directly I am writing. So limit h tends to 0. Okay, f of x naught plus h, so 0 plus h, comma y naught 0. minus f of x naught y naught 0 comma 0 divided by h. Okay, now this is, so f of h comma 0, wherever x there you write h, and wherever y there you write 0. Therefore this will be 0 by h square plus 0, 0 square, so 0 only. So 0 minus, what is f at 0 0? F at 0 0 is 0 only. Therefore 0 minus 0 by h. This is limit h is reaching to 0. So answer is 0. Similarly fy at origin, okay, and dou f by dou y at origin. So this will be again limit h tends to 0, right? Variation y coordinates, so such, okay, minus f of 0 comma 0 whole upon h. Now this is f of 0 comma h. So wherever x there 0, wherever y there h. So denominator 0 square plus h square. So simply h square denominator, numerator 0. 0 by h square is 0. So limit h tends to 0, this is 0. So 0 minus 0 by h. Answer is 0. But what I want second order partial derivatives at origin, right? So for that what I am doing is, so fx, so doing derivative with respect, partial derivative with respect to x, therefore first you substitute x point, but don't substitute y, because you are proceeding for second order partial derivative. Okay, listen once again. This means fx, partial derivative of f with respect to x at 0 comma y. Since y at this point, because we need to proceed further. Further means with respect to y, again I need to proceed this, because I want fxy. This one I want fxy at origin. So now here with respect to x you are doing, therefore at x I am substituting. At y I should not substitute, because with respect to x I am evaluating. Okay, now y as it is I am keeping. So again by using definition, what is this? Limit h tends to 0. H tends to 0. What is this now? So limit h tends to 0. F of variation in x. So x naught plus h, right? So let me write that. Then I will substitute x naught plus h comma y naught minus f of x naught y naught. X naught y naught upon h. Okay. Now this one, yeah, limit h tends to 0, which is reaching to 0. F of, what is x naught? Origin. X naught is 0 here. This is x naught, this is y naught. Okay. So x naught is 0 plus h. What is y naught value? Y naught value is y only. So 0 plus h comma y minus f of x naught value 0, y naught value y upon h. That means this value we need to compute. That means h comma y and f at 0 comma y. So first function is x into y, 2x square minus 3y square upon x square plus y square, when x comma y is not equal to origin. If it is equal to origin, it is 0. So this is f of x comma y. Then in this you have to substitute all these things. Okay. So let me continue this. So this is, simplify that. So limit h tends to 0, which is reaching to origin. Okay. And what do you get? F of 0 plus h is h comma y minus f of 0 comma y whole upon h. Okay. Now in this you have to substitute. So before that I want, what is the function? What is the function? F of x comma y is equals to x into y. X into y, this is the numerator, 2x square minus 3y square, isn't it, divided by x square plus y square. So this one when x comma y is not equal to origin, right? Now let's substitute back in this. So wherever x, there you write h, wherever y, y itself. Therefore this one h into y. So limit x tends to 0, h into y, and 2h square minus 3y square whole upon h square plus y square. Okay, this one minus f at 0 comma y. So now instead of x you write 0, instead of y, y itself. Therefore this is 0 whole upon h. Okay. Now let us apply the limit. So limit h becomes small, and as h tends to 0, simplify this. So limit h tends to 0, h is reaching to 0. Look at this h and this h will cancel out, this h and this h. So finally what will remains here? Y into 2 times h square minus 3 times y square upon h square plus y square. Okay. Now substitute back. H is 0 in this. H is 0. So y into 0 minus 3y square, or h is 0, only y square. So y is out, one y will remain, and this y will cancel out, minus 3y will get. So therefore this is what fx, isn't it? Fx at 0 comma y. This value is how much? This value is minus 3y. Okay, so assume this is 1. Now let us proceed fxy. Now same thing only for this function only, but with respect to y I am proceeding. With respect to y, that means, listen carefully, don't get confused. Let me write clearly. So fx of 0 comma y. So this function I am doing derivative with respect to y, and substituting back y is equal to 0. That's it. So initially what I did with respect to x, I have done the partial derivative and x is 0 substituted. Now with respect to y I am doing partial derivative and y is equal to 0 I am substituting. So this is indirectly fxy at origin 0 comma 0 only. Okay. According to definition again, limit h tends to 0. Which function now? Fx at 0 comma y, how to take fx. So now what is that fx? So fx now varying in where? Y coordinate. So x naught comma x naught y naught plus h. Let me write this one. After that I will substitute y naught plus h minus f of x naught y naught. X naught y naught. Okay. Upon fx, this is fx upon h. Okay. Now this is limit h is becoming small, that is 0, fx. So now what I need to substitute? Fx at already x naught is 0, right? X naught is 0 already. Y naught is, now I am substituting 0, so 0 plus h. Okay, minus fx at 0 comma 0 whole upon what? H. Now so this is fx. Yeah, let me write this clearly. Limit h tends to 0, fx 0 comma h. Okay, minus fx 0 comma 0 divided by h. Now look at this. Look at this fx 0 comma h. Look at this is fx 0 comma y. So instead of y you are having h. That's it. So wherever y, there you write h. So minus 3. So this value is minus 3h. Fx 0 0 means what? Fx 0 0. 0 0 means what? Y value should be 0. Already x is substituted 0. No need to worry about this. Only y coordinate you have to substitute. Here y coordinate should be h. Here y coordinate should be 0. So that we are going to substitute. So then what will you get? Minus 3h, isn't it? So therefore minus 3h limit h tends to 0, minus 3h and minus 0 by h. What do you get? You will get minus 3. So therefore conclusion, fx y at origin is minus 3. Or if you are getting confusion with this kind of notations and calculations, simply function is already given to you. So this is a function, look at, so this is a function, this is a function, take this function find out what is fxy simply by u by v technique, and you will get perfectly what is fxy. Then after that you substitute 0 comma 0. That's it. This is second method. Okay. Yeah. Next one, fyx I want, right? Fyx. So fyx, that means first with respect to y. Okay, first with respect to y, after that with respect to x. So first with respect to y I want. First with respect to y. After that what I have to do? Since with respect to y you are doing, therefore y coordinate is substitute, x coordinate is as it is, x comma 0. So this one is a question mark next. So by definition, limit h tends to 0 with respect to y, therefore variation in y. So f of x naught comma y naught plus h. Okay, minus f of x naught y naught upon h. Now this is, so limit h becoming small 0, and what is x naught value? Instead of x naught you substitute x, instead of y naught you substitute 0. So x comma 0 plus h. Okay, minus f of x naught is x, y naught is 0, x comma 0 upon h. Okay, again let me write the function here. What is the function? X into y, f of x comma y. X into y, 2x square minus 3y square whole divided by x square plus y square. Okay, then substitute back here. So limit h becoming small, h tends to 0. Yeah, what do I want? F of x comma h. Wherever x, there you write x only, but instead of y you write h. So x into h, instead of y I am writing h. Okay, 2x square minus 3h square divided by x square plus h square minus f at x comma 0 is 0 divided by, because y coordinate is opposite, x square plus h square. Okay, yeah. Now this one, so simplify this. Limit h tends to 0. Yeah, what is this now? So x and h, sorry, this is only h, right? This is only h divided by h, this one divided by h. Okay, limit h tends to 0. So this h and this h will be cancelled out, h and h is out, h and h. So x into 2x square minus 3h square upon x square plus h square. Okay, now this become, so substitute h is 0. So substitute h is 0, then what will you get? X into 2x square, x into 2x square divided by only x square. So what will remains? Square is out, you will get 2x. Okay, so therefore fy at x comma 0 is just 2x. Okay, x square is out, only 2x will remain. Next, with respect to x I have to do, right? So with respect to x, here with respect to x I have to proceed. Let me do it here itself, or if you want you can take it itself. I will play from here. So fxy, so fy at x comma 0, this one I am doing 0, and this function again I am doing derivative with respect to x, and after that substitution of x is 0. So this is exactly equals to fyx, first with respect to y, next after that with respect to x, fyx at 0 comma 0. It is exactly equals to this one. So therefore, and this is equals to, yeah, limit h tends to 0, same like previous one. With respect to y you are doing, with respect to x, right? Sorry, with respect to x you are doing. So fy function is same, fy only. Now you have to take this function into consideration, and this function, this one with respect to x you have to do. Okay, now fy x coordination variation, therefore x naught plus h comma y naught minus f x naught y naught, okay, divided by h. Then what will you get? H tends to 0 here. Okay, so limit h tends to 0, okay, and fy, and here also fy, right? This is fy x naught y naught. Okay, so fy x naught already 0, 0 comma 0 plus h comma 0 minus fy at 0 comma 0 whole upon h, and this one fy, yeah, so limit h tends to 0, fy h comma 0, so fy h comma 0, that means wherever x there you write h, so therefore what will get? Limit h tends to 0, yeah, 2h, right? This is 2h minus 0 by how much? H. So what will you get? H cancel out, so limit h tends to 0, we will get 2. Answer is 2. So this is fxy at 0 comma 0, and this is fxy at 0 comma 0, so this one. So both are not equal. This is minus 3, that is 2. Okay, so therefore finally, so this one what I can write, so therefore xy at 0 comma 0 is how much? 2. So therefore yx, right? Sorry, fyx, this is fyx, so fyx at origin is how much? 2. So therefore finally both are not equals. Which one? So this one, so this one and this one, these two are not equals. Okay, hence proved. Next, continuation on theorem number 1, the mixed derivative theorem, that is Claret's theorem. If f of x comma y and its is a two variable function and its partial derivatives fx, fy, fxy, fyx are exist, that means first order and second order partial derivatives are defined throughout an open region containing a point a comma b. It means, for example, consider this. So I am taking a region like this because in 2D the region is like this. In one dimensional, region means it is an interval on x-axis, right? In two dimensional, region means a disk, right? Now this is a disk, and in this disk the point, this point is a comma b, this point is a comma b. It's what here, look at once again, and these partial derivatives are defined throughout an open region containing a point a comma b. So this is a region, so it is open region, therefore you write dot dot. So boundary is not included, so it is an open region, so dot dot dot, only inside portion. Okay, and in this region a comma b is containing. So in this region these functions are well defined. That means indirectly, if all these functions are bounded indirectly, if these are bounded, in this region, then what is the conclusion? Fxy at a comma b or fyx at a comma b. What is the difference between these two? First partial derivative with respect to x, after that with respect to y, but here first with respect to y, next with respect to x. That means order is changing, look at. But whenever these functions are bounded, then these two must be equal. That means first with respect to x or y doesn't matter, both fxy and fyx are at the point a comma b are equal. That is, the order of differentiation is immaterial. That means they will not change. Either you can do first with respect to x or you can do first with respect to y. That is true whenever all these partial derivatives are bounded. If they are not bounded, then these two are different. That means fxy, fyx, the functions will become different. That means if you do fxy, sometimes you may get some x square plus y, for example, and if you do fyx, you may get some 2xy plus y square, like this. If they are not bounded, if fxy, fyx are not bounded, you get like this differently. But if they are bounded, you will get same, like fxy, for example, x square 1, x square plus 1, and fyx again will get x square plus 1, like this. You will get same if all the partial derivatives are bounded in this open region. Okay, next, derivative of a composite function and implicit functions. By chain rule you have to do, look at this. If y is equal to f of x be a single variable function which is differentiable function, and x is equal to x of t, that means this function x is again function of x of t. That means it is an implicit function. Okay, it's like, you know, for example, f of x is equal to some sin x. Okay, where x is t square plus t, like this. That means indirectly this is what? Indirectly this is f of x is equal to sin of t square plus t, right? Indirectly, that's it. Sin of t square plus t. So this is the original function actually. So x is again you are redefining. That means it is implicit function. Indirectly this one. So y is equal to f of x be a differentiable function and x is equal to x of t. Then how to find derivative dy by dt, because now overall f is a function of t, right? Here f of x is nothing but y, you can write, no problem. Y is equal to f of x, or simply y is equal to f of x. Now y is a function of t. Y is a function of t. That's why dy by dt I am doing, because dy by dt. How to find dy by dt? But initially y is a function of x. That's why dy by dx. Y is a function of x, dy by dx. But x is a function of t. So therefore dx by dt. First y is a function of x, that's why dy by dx. Next this x is a function of t, that's why dx by dt by chain rule. Okay, like, you know, for example, f of x is equal to ln x, ln 2x. Already I told you this. ln 2x. What is dy by dx? df by dx. df by dx means it is 1 by 2x. Again 2x derivative, right? That means d by dx of again 2x. That means which is 2. One more time you are doing derivative. Same thing. dy by dx, again x derivative is dx by dt, like this. Now if you cancel out dx and dx, you will get dy by dt only. Look at dy by dt only. If you cancel out these two, look at dx and dx will be cancelled out. What will remain? dy by dt only. dy by dt only. Okay. So this is proceeding by using chain rule. Okay. Similarly, next one, for the function of two variables, this is function of one variable. If z is equals to, okay, so if z is equal to f of x by a two variable function and all the partial derivatives exist, and this x is x of t and y is y of t, so both are functions of t, then how to proceed? dz by dt. Now overall z is a function of t now, because x is a function of t, y is a function of t. Again same story. First initially z is a function of two variable, right? That's why partial derivative will come, dou z by dou x. But here y is a function of single variable x, that's why dy by dx I am writing, not dou y by dou x. When the word dou will come, if there are more than one variable. I think it is clear now. So since z is a function of two variable, therefore dou z by dou x with respect to x you are doing means y is constant. Okay, and again x derivative is dx by dt, because x is a function of t. Plus, why I am writing plus? Because z is a function of two variable. Here y is a function of one variable, therefore there is no plus here. If y is a function of two variable, again plus one more variable I have to do. But here one more variable y is remained, therefore plus dou z by dou y, that means x is constant, and y derivative dy by dt. That's it. And for the function of three variables, same story. If w is equal to function of x, y, z, the three variable function and all the partial derivatives exist. Okay, yeah, all the partial derivatives exist, and x is a function of t, y is a function of t, and z is a function of t. Then how to find df by dw by dt? Again, since w is a function of three variables, therefore three times you have to do differentiation. So first dou w by dou x with respect to x and dx by dt. By chain rule, x derivative is dx by dt because x is a function of t. And again dou w by dou y, and y is a function of t, dy by dt. And dou w by dou z, and z is a function of t, like this. So whenever implicit functions are exist, a function is defined implicitly, then we can apply this technique to find the derivative or partial derivatives. So let us look at this. Look at this problem depending on that implicit function. So now here f is a function of this and x is a function of t square plus 1. So this you can do directly like this by first method, means f of x comma y. So f of x comma y is x cos y, okay, plus e raise x into sin y. Now I am substituting x is equal to t square plus 1, y is equal to t square plus 1. X is t square plus 1, wherever x, there I am writing t square plus 1, comma, y is t cube plus t, t cube plus t. Okay, now substitute here t square plus 1 into cos of t cube plus t plus e power x t square plus 1 into sin y, sin of t cube plus t. Now it is a function of t now. So overall f is a function of t. So So let me write it as a single variable function now, f of t, that's it, because it is single variable function, this one. Now you can proceed what is df by dt. Okay, that means do derivative with respect to t. After that substitute t is 0 at the end. Okay, UV method you are supposed to apply. This is first method. And second method, by chain rule, just now what we did. Yeah, second method, what do you want, df by dt, right? So df by dt, since f is a function of how many variables? F is a function of two variables, x and y. Therefore first dou f by dou x, and again dx by dt. Why dx by dt? Because here dou I am using, because f is a function of two variables. Here I am using d. Why? Because x is a function of single variable t. Because x is a function of t, x of t is t square plus 1. Only one variable, that's why dx by dt. Plus again dou f by dou y. Again by chain rule, dy by dt. That's it. After complete evolution of this, you substitute t is 0. First, what is dou f by dou x? Dou f by dou x. So this is f with respect to x you have to do. So first let me write dou by dou x of what is f? F is x into cos y plus e power x into sin y. Okay. Into dx by dt. What is dx by dt? So 2t. Dx by dt is 2t. Okay. Next plus dou f by dou t. Dou f by dou y, sorry. Dou by dou y of what is f again? X cos y plus e power x sin y into dy by dt. What is dy by dt? Into, I am writing into 3t square plus 1. T derivative is 1 into 3t square plus 1. That's it. And simplify this, what you will get? So dou by dou x of this with respect to x, therefore y is constant. So only cos y plus with respect to x, e power x derivative e power x only sin y. Okay, into 2t. If you proceed by this second method, steps may decrease. Here you look at UV method, you have to apply first UV method here, and again chain rule you have to apply. Here also UV method, again chain rule you have to apply. So some steps will increase here, but here we will get a less number of steps here. Next dou by dou y. So minus x into sin y. Minus x into sin y plus with respect to y. So e power x cos y and 3t square plus 1. Next one what you have to do is, so now derivative is over, partial derivative is over. Next replace y value. Y value here how much? T cube plus 1. Look at the problem. Y value is t cube plus t, x value is t square plus 1. That you substitute back here. Then what you will get? Cos of what is y value? Y value is t cube plus t. Therefore cos of t cube plus t. Okay, plus e power x, e power t square plus 1, t square plus 1 into sin y, sin of t cube plus t, t cube plus t. After that into what I have to do? 2t, 2t I have to write. Same thing for this. So minus x value, t square plus 1, t square plus 1 and sin y, sin of y. What is y value? T cube plus t, t cube plus t. Okay, and plus e power x. So let me write this in the next page. T. This is over, and 3t square plus 1. 3t square plus 1. Okay. Now this is df by dt. Next one, what I want? Df by dt at t is 0. At t is equal to 0. Now substitute wherever t there is 0. Then direct. So cos 0 1 plus e power 0 1 into sin 0 0, right? Into outside 2 into 0 0 plus, and here minus of 1 0 plus 1, isn't it? Plus sin 0 0 plus e power 0 1. So 1 into cos 0 1. Alright, overall outside 3 into 0 plus 1, 0 plus 1. So now what you will get? So this is 0 and here 0, 1 into 1, so plus 1. So answer is 1. So therefore df by dt at t0 is 1. You can do like this, or you can evaluate directly what I did by first method. You can do like that. So, but if you proceed by first method, you will increase some more number of steps. Okay, next one. Problem 11. Find df by dt at t0, where it is a 3 variable function. Again same story. So let me start and you continue this. So df by dt. Now what is df by dt? Since f is a function of 3 variables, so first dou f by dou x. Again by chain rule dx by dt, because x is a function of t. Okay, plus again dou f by dou y, and y is a function of t, so dy by dt. Okay, plus again dou f by dou z, because it is a function of 3 variables, right, and dz by dt by chain rule. That's it. So substitute all the unknowns and at the end you substitute t is 0, same like problem number 10. So take this one as exercise, try with your own. Okay, next one. Total derivative, a new concept. So let z is a function of two variables, and all the partial derivatives exist for z. Then total derivative is defined as this one, dz is equal to fx into dx plus fy into dy. Fx means partial derivative of f with respect to x, and partial derivative of f with respect to y is fy. So this is called total derivative by definition. Okay, so now look at one problem depending on that. So yeah, so what I want, so z is f of x comma y, right? So this is dz is equal to, or df is equal, you can write like this also, or you can write, since z is equal to f only, right? So dz is nothing but df. You can write like this also, df is equal to fx dx plus fy dy, like this. So before this I want what is fx and fy, right? Now what is fx? Now partial derivative with respect to x. That means what, dou by dou x of the function ln of cos xy, cos xy. Okay. Now what is this with respect to x? Therefore y is constant, so 1 by cos xy first, 1 by cos xy, and again cos xy derivative minus sin xy. Okay, again xy derivative, see two times. First of all, ln derivative is 1 by cos xy, and cos xy derivative is minus sin xy. Again inside xy derivative with respect to x is y, so this is finally fx. Okay, and what is fy? Again same story, so dou by dou y of, okay, ln of cos xy, right? And now again first with respect to ln derivative 1 by cos xy, 1 by cos xy, again by chain rule cos xy derivative minus sin xy. Okay, minus sin x, minus sin xy, and again xy derivative with respect to y, it is x. So this is fy. So now finally dz or df, so therefore total derivative df is fx. What is fx now? Minus y into sin xy, minus y into sin xy divided by cos xy. Okay, next plus fy, so minus x into sin xy divided by cos xy, and here dx, here ty. That's it. So you write this one. So first you have to substitute in this. So this is total derivative, df is equal to fx into dx plus fy into dy. So in this I am substituting back. So df, and fx means this one into dx plus fy means this one into dy. So this is total derivative, and when it is useful in the next semester, even semester 2, you are going to solve this kind of differential equations, differentials. So before that we are constructing how to construct such equations. So by using this formula we can construct such equations. In the next semester you are going to solve these equations for f. So now this, in this, what is unknown? Unknown is f. Now we are going to find what is f in the next semester. Okay. And I want to recall one problem. I have given one exercise in the last class, that is f of x comma y, which is some x square plus y square divided by tan xy. I remember this problem. I have given this as exercise, and whenever x comma y is not equal to origin, and this function value is 0 whenever x comma y is equal to origin, and verify the continuity, right? Verify the continuity at origin. Hope you have done this. Continuity at 0, 0. Okay. I think you have done this. Just I am recalling this solution. You proceed like this, since so x naught y naught is origin 0, 0, right? Now first point, what is that? F of x naught y naught is, f of x naught y naught value is, that means f at origin, f at 0, 0 is defined as 0. Look at this, 0, f x comma y is 0, 0, function value 0. That's what I am writing directly 0. And second one, we are supposed to find the limit. So this is the main thing here. So limit x comma y reaching to origin of the function, what is that? X square plus y square by tan xy. So if you substitute directly x is 0, y is 0, you will get 0 by 0 form. So therefore it seems to be either you can simplify the function f of x comma y, or you can approach via path limits. So you cannot simplify this function, the max I am writing along y is equal to mx, because y is equal to mx, the path will reach the origin 0, 0. Okay. Or simply y is equal to x, you choose your wish. Y is equal to x also you can choose. Y is equal to x. So therefore let me write y is equal to x. So if you write y is equal to x, what it becomes? So this is equals to, so this is, so limit x comma y reaching to origin 0, 0 along y is equal to x, So therefore y is equal to x, then substitute x square plus again x square divided by tan x square. Okay. Now this becomes 2x square, so 2 will comes out. So limit x comma y is reaching to origin, and x square by tan x square. Okay. And this again, right, 2 is comes out. So limit x comma y reaching to origin. Okay. And this I can write 1 by tan x square by x square I can write. Okay. Tan x square by x square. So this will be, so 2 into 1 by, so limit will come down. Limit x comma y reaching to origin 0, 0, tan x square divided by x square. Okay, this entire thing is in denominator. Okay, so now this will be 2 into, right? Yeah, this. Yeah, now we substitute x is 0, y 0, you get again 0 by 0 in the denominator, right? So again, since it is single variable function, therefore we may go to the L'Hospital rule. So limit x comma y reaching to origin, right? Tan x square derivative secant square x and x square derivative 2x by chain rule. Okay. So this will be, yeah. So secant square x, tan x square derivative secant square x square, and x square derivative is 2x divided by, and x square derivative is here 2x. Okay. Now this 2x is out. Now 2 into apply limit x is 0, secant square 0 is 1, so 1 by 1, so you are getting 2. So therefore limit value what I got, so limit x comma y reaching to origin 0 comma 0 of the function f of x comma y, you are getting 2, limit is 2. So therefore third point both should become equal, right? But it is not becoming equal. Therefore third point what I want, so limit x comma y reaching to 0 comma 0 of f of x comma y, f of x comma y is not equals to f of 0 comma 0, that is this is 2 which is not equal to 0. So therefore f is not continuous at origin, f is not continuous at 0 comma 0. So like this you can proceed, because some of the students are asking this one, sir, how to proceed this. So this is a way of doing like this. Or you can take y is equal to mx also. So you take a classroom and you investigate all the chairs about whether they are good or bad. So in this what you have to do, pick up at one chair, that's it. For example, I am picking up one chair which is not good, then that is enough. Therefore I can say that the chairs are not good in this classroom. Just to take one chair, that is enough. If the chair is not good, then in this class the chairs are not good, that's it. Same thing, pick up one path such that limited that value is not equal to original value 0, then I am done, f is not continuous, that's it. And so therefore here 0 comma 0 is discontinuity point, right? Now removable discontinuity means, look at in this problem, instead of 0 if I am defining this one as like this, so same problem only, instead of 0 just you write 2. Now it is continuous at 0 comma 0, right? Because f at 0 comma 0 you are getting 2, limit value also I am getting 2, therefore 2 is equal to 2, therefore continuous. So therefore by redefining this function became continuous at origin 0 comma 0. Therefore such point 0 comma 0 is said to be removable discontinuity. Therefore 0 comma 0 is removable discontinuity. That means what, this point may be removed from discontinuity by defining like this, by redefining 0 value should be 2 like this. Therefore 0 comma 0 is said to be removable discontinuity. Such point we can remove by defining the function like this. Now if we are defining like this function becomes continuous. Therefore here the point 0 comma 0 is removable discontinuity. Before that it is discontinuity point, particularly it is removable discontinuity. Okay, so this is about removable discontinuity and this one. Okay, and with this I will stop.